Hello everybody, this is Philipp Jonas for Kalamazoo Valley Community College, and today we're going to talk about economic production and growth. In our course on macroeconomics, economic production and growth refers to how countries grow their standard of living over the very long term. The difference in average annual growth rates might only be 1 or 2 percentage points, but over the years, through the power of compounding, these differences in growth rates can lead to really big differences in the standard of living of a country. In fact, a Nobel Prize-winning economist once remarked, once you start thinking about economic growth, it's hard to think about anything else. Let's start out by looking at a couple of numbers. Here's a selection of countries and their GDP growth, corrected for both population and inflation over a very long time period. For all of these countries here, at least 100 years worth of economic growth, which of course leads to some questions about how GDP is estimated before it was started to be tracked in the modern method. But the overall point stands. There are two major facts that I want you to pay attention to here. Number one, if you measure a standard of living as GDP per person, we see big differences in the standard of living across the globe. Now, of course, there is a caveat here that GDP per person isn't perfect when comparing countries at different levels of development, so the difference may not be as big as these numbers suggest, but it certainly exists. And then number two, when we look at average annual growth rates over a long time period, we see that those two vary quite a bit. And that's what we're going to be learning about in today's lecture. How in economics do we think about this variation in growth rate, since it makes such a large difference over the long haul? We will start out by learning the traditional model of economic growth. It's a very mathematical model that's been around for almost 100 years now. And it has a very important, very strong conclusion. Basically, that a country that begins with a lower GDP per person level is able to grow faster than a country that already has a high rate of GDP per person. Picking two countries from this list here as an example, it explains why over this long time period, China is able to grow at a faster rate than the United States, because it's starting from a lower point. So it will catch up with the richer country over time. But as powerful and hopeful as this mathematical model is, it also has a bit of a blind spot in that while it's possible for a poorer country to grow faster, this doesn't always take place because of a lack of what we nowadays refer to as economic institutions. And we will talk about their importance in the second half of this lecture. So let's start out with the traditional model of economic growth, which really is all about one word: productivity. You've probably heard this word before. Productivity refers to, for every unit of effort that workers are expending, how much goods and services ends up being produced. Now, typically, productivity is measured as output per hour worked, but to keep the math a little bit simpler, let's just define it as output per worker. So basically, what if workers in all countries worked an equal amount of hours, which of course isn't true, but again, isn't necessary for getting us to the conclusion of this mathematical model. So in economics, then of course, when we look at this building of a mathematical model, we try to find the smallest number of variables different between countries that can explain a maximum of variation in this productivity measure. And it turns out, depending on how you count, there are about 4 major contributors to a country's productivity. None of these will come as a surprise, but let's learn about them in order. Number 1, capital, which in the context of economic growth is also referred to as physical capital in order to distinguish it from another term we'll learn on the next slide. Capital, of course, in economics refers to equipment and structures that can be used to make goods and services. Countries that have more physical capital per worker, more K over L, notice we abbreviate capital using the letter K in economics, C is already taken for consumption. Countries that have a higher level of capital per worker have a higher level of productivity. In other words, if you happen to be born in a country where you will go to work in a high-tech, well-equipped factory, you will be able to produce more than if you were to go to work in a place that maybe doesn't even have a factory, where you're doing piecework by hand. Number 2, the reason we call capital often physical capital in economic growth is that human capital is also very important for a country's development. Human capital, abbreviated H. Human capital refers to the skills and training of the workforce. You yourself can think of yourself as acquiring human capital right now. By learning, you raise your productivity, which will raise your value to your employer, which will hopefully result in you being paid more. Countries that have a higher degree of human capital per person see higher productivity. Number 3, natural resources. Natural resources refer to the actual inputs into the production process. For example, if you are making tires, you might need some oil to do that, you might need some land to locate that factory, and so on and so forth. Countries that have higher natural resources per worker tend to be more productive. Although this one is not as important as we once thought. If I were to talk to an economist from a century or two ago, they might say that a country that doesn't have natural resources would face a barrier to development that might be almost impossible to overcome. Let's point at 2 countries that are famous examples of the effect on natural resources on how rich a country is to see why that's no longer as true as we once thought. The first country would be Saudi Arabia, which in some ways has won the natural resources jackpot. Not only does Saudi Arabia possess a lot of oil, it's very easy to get out of the ground and onto a tanker ready for export. So of course, this is the reason that Saudi Arabia is as rich as it is. Great natural resource abundance. But then let's look at another country, Japan. If you were to look at it in terms of a map, from a natural resource perspective, Japan is not in a great spot. It's not that big of a country, mostly mountainous, nothing too exciting in those mountains, maybe a little bit of coal. And of course, there are geographic problems with fault lines and earthquakes as well. Just looking at the map, seems like a tough place to have a modern economy. But of course, Japan is one of the most advanced economies on the entire planet. Why? Because of the reasons we've already discussed. Great physical capital, some of the best factories on the planet, great human capital, one of the best trained workforces on the planet. And natural resources, they've become a lot cheaper to ship. So you can now import those if you don't have them yourself. Of course, it's even better if you have them yourself, but again, it's no longer that barrier to development. So you can think of the economist's perspective of a country's productivity as basically being 3 major ingredients we throw into the pot. Number 1, the equipment, the structures, that's the physical capital. Number 2, how well trained our workers are. Number 3, the natural resources we have available in our country. But then there's a 4th factor that explains how much productivity this stew can generate. and that's what we call technology or technological knowledge. It refers to what we know about how to produce products. Technological knowledge is, over the very long term, the reason that we are so much richer than, let's say, people 2,000 years ago. It's not like they were any less hardworking. Make sure to separate technological knowledge from human capital in your mind. Technological knowledge is across our society. What do we know is possible? What do we know and how it can be done? Human capital refers to how trained that workforce is. So in some ways, what we have embodied in those workers in terms of knowledge. Explaining this another way, technological knowledge has to be invented once, and then it continues to exist and can be used by anybody. Human capital is something we have to train. With every new generation, we have to, in some sense, start from scratch and build up that human capital again. That's why we call it human capital. It's similar to physical capital. You have to build new factories on a regular basis as well. So those are our major ingredients for explaining productivity. And we build a mathematical model around these that's called a production function. If you've already taken a course in Macroeconomics, you might be familiar with the idea of a production function. This is also what we use to describe how an individual business produces goods and services. But now we're going to use a production function to think about how an entire country produces output, that is to say, GDP. And we're not going to start out with having this production function be on a per person basis. Up until now, we've talked about capital per person, natural resources per person. We're going to start out with the amount of production for the entire country. All inputs go in, total output comes out. Okay, so right now, you're just looking at a number of algebraical symbols. Y equals A times F of L, K, H, and N. Now, each of these means something specific and uses standard abbreviations. Let's start with that F. That's the standard mathematical symbol for a function. That's the thing we actually mean when we say the production function. Now, it describes how the inputs of a country, L, K, H, and N, are produced into output. You can imagine that when you actually carry out this type of mathematical economics, trying to measure what inputs a country has, and then mathematically describing how that becomes GDP, the math becomes quite exciting. In fact, there's an entire subfield of economics, econometrics, that deals with operationalizing this type of math. We're not going to do this in our course. We'll just leave this production function, F, as a function. There exists a type of math, and you can put measurable inputs for a country in there, and it predicts how much output this country produces. F, the production function. Then there's a letter here we haven't encountered yet, A. For historical reasons in economics, A is the letter we use to denote our level of technology. Not terribly intuitive, maybe think of it as advancement to remember it. Now notice that technology sits in a very special point in this equation. It's the one thing that is outside of the production function to show how much output a country generates. In other words, it's not an input per se, but rather it's a factor that multiplies what our production function does. So what that means is there's basically two ways in which a country can produce more. A Approach number one is if you have more inputs, if you have more workers, more physical capital, more human capital, more natural resources, your country can produce more. But option number two, much more exciting in some ways, is this letter A. If our technological knowledge increases, if A gets bigger, we produce more GDP without needing more inputs because it sits outside of the production function. Technology is the thing that allows us to get more GDP without needing more inputs. That ends up being very important. But first, let's get to know this production function a little bit better. As I mentioned, we're not going to do the actual math of how these production functions are specified. But there is something you have to know about how they behave. A mathematical property. It's called constant returns to scale. A production function, if you increase how much you put in inputs, its output increases by the same percentage. Not all mathematical functions behave this way. For example, an exponential function. If you increase input, output increases by much higher percentage than how much you increased input. Exponential functions have this explosive growth. That's not how production functions work. They have, if you will, proportional growth. Although again, that's technically referred to as constant returns to scale. So for example, if you were to double each of the inputs into this function, if you were to say, okay, what if this country had twice the number of workers, twice the amount of physical capital, twice the amount of human capital, twice the natural resources, how much more output could it produce? The answer is twice as much. Input and output grow at the same rate. This works for any percentage change, not just for doubling. For example, if you were to ask, what if we put 10% more input in? 10% more workers, 10% more physical capital, 10% more human capital, 10% more natural resources. How much more output do you get? 10% more. Notice that's increasing all of the inputs by 10%. I did not have to increase technology. That's because the A sits outside of the production function. Now this is a very specific mathematical property, the idea of constant returns to scale. Why are we talking about this? Well, functions that have constant returns to scale, as is illustrated here. If you multiply the inputs by a number, you multiply the output by the same number, equation still holds. It works for the number 2, it works for the number 1.1, but we're not going to multiply by either one of those. Instead, we're going to multiply by a very, very clever number. And the reason what I'm about to show you works is because this production function has the constant returns to scale property. So what are we going to multiply by? 1 over L. Per worker, in other words. So we're taking this production function that's currently at a total level. We've got the country's GDP, capital letter Y on the left hand. And in terms of the inputs, we have that country's workforce, physical capital, human capital, natural resources. Now we're going to multiply by 1 over L. So what do we get on the left-hand side? Instead of GDP, we now have GDP per worker. Hey, we encountered that at the beginning of this presentation. That's what we call productivity. So we're going from GDP to productivity on the left-hand side. And then what explains the productivity of a country? 4 variables. I'm going to go from right to left here. Natural resources per worker, human capital per worker, physical capital per worker, and technology. Exactly the 4 determinants we had talked about. 2 special notes here. Notice technology is not per worker. That's because technology can be shared by all workers. You don't need to invent something again so that more people can use it. Again, technology behaves special. It sits outside of their production function. And secondly, notice that for a country's productivity, the size of its workforce doesn't matter. The workforce in the total function gets divided by the workforce in the productivity version of the function. Those 2L cancel and you're left with a constant number 1. Again, that's why productivity has 4 determinants: technology, physical capital per worker, human capital per worker, and natural resources per worker. This is how we think about productivity. This is how we think about how a country transitions from poor to middle income to rich country using the traditional economic model. So in other words, if technology, physical capital, human capital, or natural resources per worker increase, the country's productivity rises. And it does so in a very interesting way. If we have a higher level of technology, productivity increases because it sits outside of that function. But if we increase any of the other 3, any of the 3 per worker ones, then increasing physical capital, human capital, natural resources per worker will have diminishing returns. Any extent by which we increase these 3 numbers will always increase productivity, but by a smaller and smaller amount. I'll show you a graph that demonstrates that in a second. But first let me explain why this is going to be so important. This explains why a country that is poor, according to this model, can grow faster than a country that's rich. Under this model, the country that's rich is rich because it has high productivity. And it has high productivity because it already has high numbers for capital per worker, human capital per worker, natural resources per worker. If we add to these already high numbers, it doesn't make as much of a difference. It does make a difference, a positive one, but it doesn't make as much of a difference as if we had a poor country that has low numbers there and we're adding to it. Let me use human capital per worker as an example. Think about education for a second. If we could get the level of education in the United States a little bit higher on average. Currently, on average, there's about 14 years of education per worker. So, high school diploma plus some college. Let's say we can get another 2 years on average there. So now the average worker has a bachelor's degree. This would be good for the productivity of the United States. Absolutely. But how different would our world be? Pretty recognizable compared to today. Just a little bit better. But now imagine you live in a very poor country where there's almost no schooling, widespread illiteracy even. And you can somehow institute a program that gets the average level of education up from 1 year, let's say, to 3 years. So some solid elementary school for the average worker. Now everybody can read and write and do some arithmetic and so on and so forth. The difference that increase would make if you're starting from a much lower base would be vastly bigger than another 2 years of education would produce in the United States. So these inputs, when they grow, they have a bigger impact if you're starting from a low point. While technology that's the one that sits outside of the function, that one always gets you forward at a constant rate. And intuitively, you probably know this. You know that when the United States will see its next economic boom, which will be something about how we improve productivity in our country, it's not going to happen because we add a little bit to our education or we build a few more factories. All great things, but a real boom will happen in a rich country like the United States because there's a technological breakthrough. Okay, that was enough foreshadowing. Let me show you what this looks like. What I want to demonstrate to you is that when you add to each of these inputs in the production function, the 3 that are per worker divided by L, productivity rises, but at a diminishing rate. And that's what gives rise to the so-called catch-up effect. I'm going to use capital as the example, but I could draw a graph for human capital or natural resources that would look exactly the same. Capital is just the traditional one. So we're going to show that each additional capital per worker has less and less impact on productivity. And here's what that looks like. When you graph a production function on a per worker basis, so here on the y-axis we have output, y over L, GDP per worker, aka productivity. And here on the x-axis we have one of our inputs, in our example, capital per worker, K over L. Then the shape of our production function has to look like this. I'm hand-waving the mathematical proof away here a little bit, but in case you are into math, just to let you know, because the production function has constant returns to scale across all its inputs, that must mean that it has decreasing returns to scale with respect to an individual input. Okay, with that super math nerdery out of the way, let's get back to the graph. This is what it has to look like. So here's how we think about production and growth in the traditional model of economic growth and development. If a country has low productivity, it's relatively low here on the y-axis, we think of that as being due to the country having low determinants of productivity, such as in our example, low capital per labor. Now, if we were able to raise the capital per labor in this country, get some investment going, some roads, some factories, as we increase here on the x-axis, notice we get a real big payoff on the y-axis. Big boost in productivity. Now let's look at another country. A country that already has high productivity, so it's high up on the productivity axis. We think of that being due to it having high capital per labor already. And now let's add to the capital per labor here. Again, we're going to build some roads, build some factories. Again, there's a positive impact on productivity. It is good to accumulate the capital. However, the increase in productivity is much smaller for this country that already has high productivity. Let's look at this graph one more time. And let me introduce you to the term of the catch-up effect. So oversimplifying, in the traditional model of economic growth, we've got 2 types of countries. Those that have relatively lower productivity, the poorer countries, they are at a lower point on this graph. And then the richer countries, they're on a higher point on this graph. And here's the tremendously hopeful message of this traditional model of economic growth. Over time, as we see investment in these countries, as capital per labor grows, both types of countries will grow, but the poor country will grow faster. That means over time, as they are both marching forward on the x-axis, their distance from each other on the y-axis will diminish. Their productivity will get closer to each other. The poor country over time will catch up with the rich country. And that's the idea of economic development. And that's the traditional model of economic growth. Very mathy, very few variables, tremendously hopeful message. But of course, it doesn't always work out. Yes, we see countries that have done a tremendous job catching up with the richest countries in the world. If we, for example, look at the 20th century, we could point at examples such as, you have to mention China, biggest economic development story ever told, or Taiwan, South Korea, Brazil, India, many examples across the globe. But at the same time, we also have seen other countries where growth has stalled. And this traditional model, I mean, you could say in the traditional model, okay, somehow they failed to accumulate capital, sure. But it doesn't really explain why it fails or what could be done to maybe get out of that trap. That's where we get to more modern economic growth theory and the idea of economic institutions. Basically, these are ways that exist in a country that aren't a simple mathematical formula, but that nevertheless can hold back economic growth if these institutions don't work well. Let's start with a really big one: population growth. Now, the idea that population growth has a connection to production and growth is actually very old in economics. It stretches back centuries, where we have Malthus, who we nowadays might refer to as an economist, making a famous argument about the amount of farmland on our planet. Basically, he was making a calculation where if our planet has a certain amount of farmland and it takes a certain amount of land to feed a person, and the world population is growing, all of which he knew already, then you could trace out a nice little graph of the point at which global population reaches a level where it exactly maxes out how much farmland we have, and then widespread starvation would keep population growth in check. Now, what's remarkable is he was wrong. Not because he didn't do the math right or anything. His math was solid. It, in fact, even earned economics a bit of a nickname. It's sometimes referred to nowadays as the dismal science, because the mathematical forecast of this model was so bleak. But what Malthus couldn't have known is that in between when he lived and when we lived, we had an industrial revolution, famously. And not just an industrial revolution, also a green revolution and many other technological leaps that allow us to grow an amount of food from farmland today that would be unbelievable to Malthus 200 years ago. Technological growth saved us. But the argument sounds solid, right? Fixed resource, growing population, eventually trouble. And one such problem, for example, can show up in economic growth. What does the traditional model say? Hey, we got to get those ratios up. For the country to develop, we want higher capital per labor. Now, in the graph I just showed you, I said, okay, if we invest in the country, if there's more capital, then capital per labor grows. Yes, if we assume that the population is constant. But what we're looking at here is a ratio. So if the population is growing at the same rate as our capital, or maybe even faster, we're not getting that forward movement on the x-axis. And it's not just physical capital that has this. Human capital, for example, as well. again explaining it more of a narrative way, even if we increase our investment in the education system, population growth might soak up all that increased investment without getting us more education per person out of the system. So here we are with our first economic institution. You can already tell the conversation tends to get much more difficult here. So for example, on average, countries with faster population growth tend to have lower educational attainment. So what can be done about that? Well, some developing countries might choose to try to change the rate of population growth. We could, for example, mention here China's one-child policy, which is complex enough that one could take an entire course on it on its own. Or perhaps on somewhat milder levels, we could talk about making contraception more widely available. Or, really nice, if you make sure women have access to education equal to men, in case there's a problem with that in the country you're looking at, it turns out the more educated women tend to be, the fewer babies they tend to have, because it raises the opportunity cost of having children. And that's how you might overcome this obstacle. Well, at the end of this particularly depressing topic, I do have a shining ray of hope. Let's get back to Malthus and global population. We still have that concern, right? Growing population, fixed resources, big problem. But since Malthus, there's also been some additional hope, because what saved us from Malthus? The fact that we had much faster rate of technological progress than during his lifetime. And there is some evidence that us having a higher population to begin with gave us that higher rate of growth. Because remember, technology sits outside of the function. You have to invent it once, then everybody can use it. So if you have more people, you might surmise that you will have more inventions, because more people will be working on inventing stuff. And to the extent that that is true, having a greater number of people might actually boost economic growth. Again, there are some famous studies here that actually underline this. Michael Kremer is something I would especially encourage you to check out, with some fascinating arguments about 1 million years of economic growth. I'm not making that number up. 1 million years of economic growth. And of course, for any of you with environmental concerns, there is a limit to this, right? Like there is a limit to how far more population will actually save us from more population, but it means that we don't quite have to think of ourselves as a dismal science anymore. So what else do we have when it comes to economic institutions? Health and nutrition. This didn't get nearly enough coverage in economics 100 years ago. But it turns out that health and nutrition are very much a type of human capital, just like a traditional education system. In fact, and this is where it gets depressing again, especially if children are malnourished, this leads to developmental deficits that you can never make back up. If you've got a malnourished child, you can't feed them twice as much as an adult and somehow erase the damage that's been done. This is, of course, for example, why in rich countries we see many programs in place now to make sure that children get enough to eat. And it's not just humanitarian, the right thing to do. It turns out that the economic returns from childhood nutrition programs are just through the roof. They so easily pay for themselves in terms of economic growth. Some famous economic studies that can be referenced here is, number one, we have the North and South Korea situation, what in economics you might call a natural experiment, where we take a country, cut it in two, have very different regimes running them. Or, for example, in retrospective, when we look at things like the Industrial Revolution, it turns out we attribute a lot more of the productivity effects of that revolution to better nutrition now than we used to. It wasn't just about the steam engine and, mining more coal. Although, of course, that was a major factor as well. Health and nutrition. Now, let's get to another one that is difficult to overcome if it's holding back a country's stability. In the traditional model of economic growth, we take for granted, if you will, that investing in a country is possible and produces good returns. Because we sort of take for granted that that country has property rights where people can control these economic resources, profit from them, grow the economy. But we know that in many countries on this planet, political instability makes life very different, where you might not be able to retain claims to your property, such as a factory. You might face revolution, dictatorial regimes that just take it from you, give it to their cronies, or even destruction. Property rights and political stability need to be in place for this wonderful story of the traditional model of economic growth to play out. But if it isn't, putting that in place is a lot harder than just building a factory. Next, trade. This is a really interesting one. So economists, by and large, are huge fans of trade, myself included. And if you've already taken microeconomics, you've learned of the principle of comparative advantage, that two countries trading with each other actually makes both countries richer. Fantastic. But it gets even better than that. It turns out free trade is also conducive for economic growth. And the reason is that countries that wall themselves off from the rest of the world, we call that inward-oriented policies. They try to limit their interaction with other countries. They don't learn as much. So we're getting back to technology here. They don't learn as much from what's happening in the rest of the world as so-called outward-oriented countries. Countries that integrate with the world economy. Especially if you're a developing country. You can really kickstart your economic growth if you manage to get your firms interacting with more developed firms so that by doing, they can increase their own productivity. And then finally, let's get back to technological knowledge itself, because that's the big one that helps everybody, and it's just about the only path left for rich countries to have large increases in economic growth still. Can't do that anymore as a rich country by building factories and roads, because even though helpful, you already have so many of them. How do you promote that technological progress itself? In the traditional model of economic growth, it's just sitting outside of that production function as a variable. And we'll just sort of assume that technology progresses by itself. But of course, it turns out you can adopt policies that promote technological progress. And because technological progress is so useful, these are really wonderful policies where, as always, you want to do a cost-benefit analysis if they make sense, but they are something that countries nowadays spend a lot of time about thinking how to get them exactly right. Because the funny thing about technological progress, what makes it so powerful, is that everybody can use it. It's what in economics we call a public good. You invest in it, and then it makes life better for everybody, not just the owner. But how do you promote investment into a public good? Well, there's actually a couple of different ways. They've got their own pros and cons, each of them. But because technological growth is so important to a modern economy, modern economies basically do all of them to see what sticks. Number one, you can try to make it more profitable to develop a new technology through patents. Basically, for a limited amount of time, in the United States, it's 20 years, for example, you say that this new technology can only be used unless it's licensed by the person who filed for the patent. That can make these patents very valuable. Pharmaceutical patents are a great example of this. This is how a lot of drug development is done. Number two, you can subsidize research and development that companies undertake. Give them tax incentives, give them cash grants, give them tax credits that they can sell. Try to make more R&D happen that way. And number three, you can have the government directly funding research. For example, through its grant programs with universities. Again, these are three examples of how to promote technological progress. They each have their pros and cons, but the truth is, modern economies do all of them, because any bit of technological progress you can get, you're really grateful for. And that concludes our lecture on production and growth. I will see you next time.